In this lecture, we're going to discuss how do we use earthquake information. And we're going to use seismic wave data to determine the Earth's interior features. So let's get this started. First off, we need to understand some basic wave properties and characteristics. We need to understand that a wave is simply energy traveling through a medium. A wave traveling through a single material travels at a constant velocity. When a wave travels into a different media, its velocity changes. When a wave comes into contact with a boundary where the media changes, it must reflect, refract, or both. And the further a wave travels from its epicenter, the smaller the amplitude or the less energy that it has. So let's make sure we identify some terminology. Reflection implies that a wave is bouncing off of a medium or a boundary, and refraction implies that it's bending through. A wave would bend through a medium or a boundary. There's some basic terminology that you need to familiarize yourself to. So if I look at this picture here, the amplitude is simply measured from this dotted line, which is considered equilibrium, to the highest point of whether it's a crest or a trough. That the amplitude is measured from here. So you'll find that this is a higher energy wave. It's got a greater amplitude, whereas this is a lower amplitude and thus a lower energy. In this case here, we can look at what we'll call an incident wave as the incoming wave. Sometimes it's going to bounce off. That's simply reflecting. Sometimes it's going to be transmitted through. It's going to bend. We call this refraction. So we'll put all of this together. And we can do that when we look at wave behavior inside the Earth. If I go back and look at the primary waves, notice that the wave velocity as it travels through this mantle is, in this case here, it's going to change as it comes into contact with this particular boundary. Now you have to think, well, before you just heard me say that the wave, if it's traveling through a single material, it's going to travel at a constant velocity. So why aren't these traveling at a constant velocity? Why is it speeding up? Well, as I travel into the Earth, we're talking about denser material. And denser material, it's going to travel faster. So as the P wave is traveling through the mantle, or the lower mantle in this case, it's traveling into denser material and thus is speeding up. But the instance in which it travels from the lower mantle to the liquid outer core, we have a phase change from a solid to a liquid, and its velocity will almost instantly decrease before it speeds up again. And so we can see these little blips in the velocities because it's traveling from different materials, different densities. Notice our S wave. Our S wave does the same thing. It speeds up, it's traveling through a denser material, and then it is not able to travel through a liquid because we know transverse waves do not travel into liquids, only in solids. So let's look at how waves reflect and refract off of boundaries. So we're going to use light just because we'll be able to observe light. So light and seismic waves are energy traveling through a media. So let's consider light traveling into this material right here. Say this is glass. Some of that energy is going to reflect. It's going to reflect off here. It's simply called the reflected ray. And some of that energy is going to refract into the glass. So if I look at A, light traveling through air hits a glass boundary. Some of the light reflects and some of it refracts through the glass. When we say refracts, it simply bends. No longer is traveling at the same angle, so it bends at a different angle. Whereas if I look at picture B, seismic waves traveling from one rock type into another rock type also reflect and refract some of the energy in the wave. So we can look at both P and S waves as they travel through the mantle. Some of this is going to reflect and some of it's going to refract. So when a wave encounters a change in material, the properties, like seismic velocities and or density, its energy is split into reflected and refracted waves. So we need to keep this in mind that we can actually observe both of these taking place for P waves, right? P waves are going to travel from our lower mantle into the liquid outer core. But we're not going to see this refraction take place when S waves travel from the lower mantle to the liquid outer core. So we can use that information and that explanation to find the depth of a boundary from reflected waves. So think of it this way. If there's an explosion, something moves rock, it creates vibrations in the Earth, and it travels from location A all the way across to location C. This is where a seismograph is going to pick up this wave. Some of that wave is going to travel into the Earth. It's going to strike this reflecting horizon and travel to location C as well. It's going to arrive later because it had to travel a greater distance. So we can look at this as if it's a triangle. If I treat A through C, I'd simply travel this total distance, whereas A to C this direction is going to be traveling at it's going to have to travel at for a greater distance. It's simply going to arrive after. Notice some of that energy is going to be refracted. We can see that. Some of that wave energy is transmitted into this boundary here, but we're not going to worry about this right now. So a controlled explosion occurs at site A. a P wave, right? P1 travels directly into a seismograph located at site C. Some of the wave travels into the Earth, what we call a body wave, and reflects and refracts at some depth that we'll call from B to D. We're going to call this a depth. The reflected P wave arrives at the seismograph after P1. So we're going to call this P2. We'll call this one P wave. Primary wave 1 arrives first. Primary wave 2 reflects, arrives after. And we can calculate the depth of the boundary from the resulting data. I need you to observe that we're going to be using triangles. We're going to be cutting this picture in half. See the dotted line? We're going to be solving for the distance between B to D. That's a depth. So it's a side of a triangle. We just created a right triangle. So that means we're going to have to do some calculations. So here's a problem from our lab manual. So we're going to solve for that depth. So this is how it actually looks, the type of problem I'm going to give you. So solve or answer the following questions. And you need to know that the velocity is going to be the distance traveled divided by the time which it took to travel there. So how fast did P1 travel? Well, it traveled from here to here, and it's this distance. And we have a time, the arrival time of P1. If the aftershock actually took place at 2:07, and P1 arrived at 2:08:36, we know that it took this amount of time to travel for P1. And P2 arrived shortly thereafter, right? We're literally talking hundredths of a second after. But that wave tried to travel here to the crust mantle, to this mantle boundary, and some of it's going to reflect. Remember, we're applying the principle here that waves are going to both reflect and refract. We want to pay attention to the reflected ray. So we're going to assume that the velocity of P2 is the same as P1. We're going to solve for the distance. We need to solve for this distance of P2. And then lastly, we're going to determine what's the depth of the surface of the crust and mantle. So we're going to use Pythagorean theorem. It's where we use a squared plus b squared equals c squared. We're going to isolate and solve for one of the sides of the triangle, and I'll do this with you. So let's solve for depth of the boundary. So here it is. So if it traveled 660 kilometers here, I'm solving for what's the velocity. The velocity would be a distance of 660 kilometers divided by the time. Now notice, we know that this took a minute 36.07 seconds. But I can't have minutes and seconds as my denominator. I have to have it all in common time. So we have to make it into seconds. So I know that 1 minute is 60 plus 36.07. So adding them together, I get 96.07 seconds. So I take 660 divided by 96.07, and I get 6.87 kilometers per second. That's a really fast-moving primary wave, but that's what happens, right? And I can convert this into miles per second simply by dividing it by my conversion of 1.6 kilometers equals 1 mile. So I could take 6.87 divided by 1.6 and get 4.3 miles per second. You will need to know how to do both of those. Okay, so we're going to assume, right? We said that we're going to assume for number 2, assuming that the velocity of P2 is the same. What distance does it have to travel through? So let's see. So now I'm solving for distance. I'm using the same equation, speed, distance, time, but now I'm isolating d. That the distance is going to be the velocity times the time. So my velocity is 6.87 kilometers per second. I simply took it from the solving for the P1. It's traveling at the same velocity. However, it took 96.94 seconds, right? A minute, 36.94 seconds to reach it. So it's slightly longer. So you're going to find that it actually traveled 666 kilometers. So it traveled from here to here. It traveled a greater distance. So P2 is going to be 666 kilometers, which if I convert that by dividing it by 1.6, I would find that it's about 416 miles. So slightly further. Remember, miles and kilometers are just different ways of measuring distance. So I have two. I have number 1, 6.87 kilometers per second, and I have number 2, which is a distance of 666 kilometers. I solved how fast this traveled, and now I solve for this distance for the reflected wave. Now we're going to put it all together. So using Pythagorean theorem. Pythagorean theorem is simply referencing a right-sided, a right angle, a right triangle. So if I know that 660 total kilometers, I can divide this and look at just this side of a triangle. In this case here, it's 330 kilometers. Or I could use this triangle. They're going to be symmetrical, so it doesn't matter. So B is the side of the right triangle we are solving for. We want to solve for this side right here. And therefore, C is always the hypotenuse, the longest side of a triangle. So according to the Pythagorean theorem, we have a side, we need to solve for a side, and we have a hypotenuse. So if I plug it in and solve it, I'm isolating B. B is going to be the square root of quantity 333, that's the size of my hypotenuse squared, minus 330, that's the side squared, and you're going to find that's 44.6 kilometers, or about 45 kilometers in depth, which is about 28 miles in depth. So this is how we go about solving the type of problems that I'm going to be asking you. You're going to have an earthquake occur, you're going to have arriving times, you're going to have distances provided, you're going to have a question of, well, what is the depth of this? And you'll have to go through this very process. So I created a practice problem for you to determine the depth of a boundary. So based on the provided data, draw and solve for the depth. And I give you an answer key. I show you how to do it. Sometimes it's worth you watching me do it. And I change the numbers ever so slightly. So here's a picture that you'll reference, but you're going to want to practice this. You're going to want to see how this gets solved. And then here's how I go about solving. I believe this is the one in the book that I already went through that I just solved for you in writing. This is me solving it with you and for you. So let's put it together, the application. Waves reflect and refract at boundaries. P waves travel entirely through the body of the Earth, whereas S waves only travel through the mantle of Earth. S waves cannot travel through liquids, so the boundary stops the S wave entirely where it reflects back towards the Earth's surface. Knowing and understanding these properties of P and S waves, we can put together a comprehensive understanding of the Earth's interior. So you can actually visualize this, and these visuals are made by complex models that geologists and seismologists put together. It's all about using the wave information. Waves are simply energy traveling through a medium. By using the data collected from seismic waves, we can determine depths and conditions of what are happening inside the Earth without actually being there to observe them directly.